Next, we'll be hearing from Pedro Salas about low-frequency radio recombination lines in the Milky Way with LOFAR.
Thank you. Hello. No. Good afternoon, everyone. My name is Pedro Salas. I'm a second-year PhD student at the Leiden Observatory. And today it's a pleasure to present to you, on behalf of the radio recombination line group at Leiden, the LOFAR survey of low-frequency carbon radio recombination lines. So, why are we doing this? Well, basically because we would like to understand the connection between the cold-neutral medium and other phases of the ISM, particular molecular clouds and the unstable neutral medium. As shown here, for example, in this example of where we have this CO cloud embedded in this H1 structure, as some of the people here already showed this morning. More particularly, what we would like to do is to constrain two-phase models of the ISM. For example, determining the gas heating efficiency as a function of gas properties. So how do we go about doing this? Using low-frequency carbon radio recombination lines. The previous speakers showed the results using high-frequency radio recombination lines, but the low-frequency ones are different in two aspects. The first one is that at the low frequencies we're tracing diffuse gas, and the second one is that since we're using lines of carbon, we find it ionized mostly everywhere, so that we're really tracing diffuse cold gas throughout the galaxy. So one of the things that the previous observations have shown is that the emission from the lines cannot be described in simple LTE terms, so that you really need to model the statistical equilibrium equations to determine how the departure from LTE affects the line emission. So our team put a lot of effort into developing updated models of carbon radio recombination line emission. In particular, this is the work of Francisco Salgado for his PhD thesis. And the optical depth is directly proportional to this beta n prime and bn. The bn describes the departure of the level population from LTE, and the beta bn the influence of stimulated emission. And since we are heavily weighted towards with temperature, we see that the lower temperatures usually dominate the line emission. So that's why we say we're tracing cold diffuse gas. Here's a comparison of the updated models with the older models from Ponomarev and Sorochenko. And in these new models, we see, for example, two interesting differences. One is that at around the n principal quantum numbers of 100, we see this bump here, mostly because of the NL treatment of the statistical equilibrium equations, and also that the beta Bn does not reach such high values as previous models. With the current telescopes, we can analyze these curves very well, since we can trace the line properties over a wide range of principal quantum numbers, which allows us to constrain these models and then determine the gas properties very well. And not only that, with modern day receivers, we can also detect a wealth of lines, which enables us to over-constrain the problem or just increase the signal to noise very easily by stacking. So just to show the power of LOFAR in doing this, I'm going to use our pilot study of CAS-A to show how this works. And just as a reminder, the line of sight towards CAS-A intersects the Perseus arm, where we can see at least two main velocity components, and also the Orion spur. And here I will focus mostly on these two components. And this line of sight is particularly well suited for a pilot study, because the background source is really bright at these frequencies. I'm talking about a couple megahertz, and also because it has been extensively studied previously so that we can compare with other tracers. So this is the LOFAR data set we have of carbon radio recombination lines, and we have detections all over the band from 78 megahertz all the way to 11 megahertz. And here we can see the two main Perseus components, and as we go down in frequency, we see that the lines get broader. We'll explain this in the next slide. And at some point, we cannot distinguish the two components anymore, so we just have to treat them as one. So the effect of line broadening is not only due to the decreasing velocity resolution of the instrument with frequency, but it's also a physical process, namely the lines get broader because of collisional broadening and also because of the Stark effect. So by using the line broadening, we can derive relations between the radiation field the lines are immersed in, I mean the carbon atoms are immersed in, and the density and temperature of the gas. We cannot, just from the line, we cannot separate these two effects, mainly because the dependence on n or frequency is very similar for both cases. And here I'm showing how the line width goes from Doppler dominated to radiation and collisionally dominated. So that provides the first constraint, and the second constraint comes from the integrated optical depth, which we can use to, in combination with the new models, to constrain the gas properties. So this is the minus 47 kilometers per second component of the Perseus arm, and we can see how the model fits the data very well, and how a slight change in electron density really produces results that do not match the observations. If we combine both constraints, the line width and the integrated optical depth, we can obtain a curve like this. And the best fit solution gives us electron temperature and density, which is with an uncertainty of a factor of 10%. So we're really proving the gas properties very well. And using the derived values for this particular cloud, we see that the thermal pressure is about 12,000 Kelvin per cubic centimeters for this particular carbon abundance. And as a comparison, here I'm showing the combined data from the Perseus arm, in contrast with the previous data from the literature, and we see that at the low frequencies, we're doing much better than previous studies. This mainly because LOFAR has a much smaller angular resolution, so that we can really start to study individual clouds. Previous observations used degree scale beams. Now we're talking about the arc-minute scales. And we don't really need to go all the way to measure all these lines. Only having 3 lines, a line that's in emission, 1 line in absorption, and having C+ observations, we can also constrain the gas properties very well, mainly because the carbon radio recombination line or the C+ line gives a very powerful thermostat. And here I'm showing as an example CAS A using PAX data, which unfortunately has a very poor velocity resolution. And we can see the temperature distribution using this. And because we're confusing all the velocity components in the PAX data and also emission from other regions in the PDR, these temperature maps are only upper limits, but it's indicative of the power of combining carbon radio combination lines with C+. And as I was saying, with only 3 lines, we can also do a very good analysis of the gas properties. So the carbon radio combination line or the C+ gives us a very good thermostat. And if we can measure 1 line in absorption and 1 line in emission close to the point where the transition happens, we can also determine the density more or less well. And if we combine both, then we really narrow down the parameter space. So as a summary, low-frequency carbon-radio combination lines provide useful information about the gas properties, in particular temperatures and densities. And this becomes even better if we have C+ observations. And for the first time, we will be able to prove how carbon-radio combination emission looks like in the galaxy using on arc-minute scales. And the survey we're carrying, we divided it into 3 strategies. The first one is using medium resolution, where the analysis is, where the data reduction is easier, where we will be proving scales of larger than 10 arc-minutes. A pinhole survey, where we will be proving scales smaller than this. We still are playing a bit with what's the angular resolution which we can really study, and an extragalactic survey, where we will study these lines in other objects. So stay tuned for more results in the forthcoming years. Thank you.
We have time for a question or 3. Do you want to go ahead?
So thank you for these beautiful results, but you did not tell us which phase of the ISM you are sampling with these lines. You have an electron density, so does the lines come from the CNM, WNM, WIM?
No, what we're sampling mostly is CNM, given the really diffuse CNM.
Then what is the ionization degree? It's a bit low.
By ionization degree, you mean the fraction of ionized of electrons that comes from carbon, or the? Oh, then sorry, I'm not familiar with the concept of.
Okay, we can discuss that later.
Thank you.
All right, oh, wait, one in the back.
This is just following up on that, but if you multiply the temperature times the density, I mean, it would seem that the thermal pressure is really low.
Sorry?
If you multiplied so I mean, this is just following up on the previous question, but if you multiplied the density times the temperature, it would seem that the thermal pressures are very low. So do you have a thought then on sort of where this is situated in terms of sort of, I mean, it would seem to be very low pressure gas, right?
Well, I thought that the usual pressure measured by, I don't know, using the C1 line was a bit lower, around 4,000. Here we're talking about 12,000.
Okay, let's thank our speaker again.